Hello and welcome back to this lecture 33 of Biomicroelectromechanical systems. I would like to briefly review what happened in the last lecture. We talked about micro mixers in details, parallel and sequential lamination mixers as passive mixers or active mixers, where there would be either chaos introduced or some kind of piezo vibration, so that there is cavitation or there is some active energy pumping into the system and there is mixing of two or more phases. We then detailed about micro valves, essentially tried to study some basics about their actuation mechanisms, their performance characterization and also specifications. So, some of the aspects like valve capacity, the leakage ratio, the power requirements, the other aspects like material selection, biocompatibility, etc., were discussed for designing micro valves or micro valving systems. We further categorize valving into passive and active valving mechanisms, and we discussed different kind of actuation mechanisms like pneumatic, thermopneumatic, thermomechanical, electrical, magnetic and some other actuation mechanisms. So, we also tried designing some of these pneumatic and thermopneumatic valving systems and saw that especially the designs have to be made in a manner which rhymes with the micro scale, and it kind of makes an area ratio between the inlet and the valve seat, so that the amount of forces that are needed for actuating the valve member is small. Okay. So, because we are talking about micro fluidic systems or micro flow systems, the inlet areas typically are small, which makes automatically the actuation forces very small, as we saw in the example about designing these pneumatic systems. We further can mount a cylinder and use the same kind of distributed load by means of hermetically sealing the cylinder and adding temperature, so that the system has PDV work, and that applies pressure on the walls and effectively a force because of this heating effect. We also talked about biomimetic passive valving mechanisms and tried to discuss about what happens to the human body, particularly in the vasculature, with a pressure gradient and the way that the valves close and open. We talked about hydrogel valves here, particularly which are sensitive to pH, and it swells and blocks or deswells and unblocks a certain flow, and flow rates can be calibrated to the pH values respectively. Today we will be talking a little more on that line about some other non-conventional valving mechanisms, and one of the most popular in the category is also electrochemical valving mechanism. So, let us see what electrochemical valves really are. Essentially a very simple system of reaction, as can be seen here. H2O is electrochemically converted into hydrogen and oxygen, and basically if you look at the overall architecture of the system, this is basically the outlet of a micro pipe, and this is a gating device here. Okay. And essentially there are 4 electrodes in this region, this region, this region and this region, and these electrodes pump in electrons so that bubbles get formulated. So, if you really control the differential of size between bubble 1 here and bubble 2 here, you can make this gate mechanism move back and forth. Okay. Suppose this is bigger and this is smaller, the gate will push back. Vice versa, if this is smaller and that is bigger, the gate will push forward, and so therefore the flow path here is kind of blocked because of this mechanism. However, this is an electrochemical valve because hydrogen and oxygen bubbles here are produced just by virtue of pumping electrons. Okay, pumping electrons, and so therefore the valve is really operated, actuated electrochemically. Similarly, you could have a blocking mechanism wherein this is the bubble which is generated by an electrode maybe, and the bubble is too big and blocks this port after a while and cuts off the flow from the inlet side to the outlet side. So, that is again called capillary force valve. There may be a tendency of the bubble to squeeze past it and go to the other direction, but we ensure a pressure gradient between these 2 points so that the valve kind of keeps here and protects the flow from going from the inlet to the outlet side or stops the flow. So that is how an electrochemical valve would operate. What is interesting for me to share here is that if we really look on a comparative basis between, let us say, a thermal setup which would generate the same bubble and the electrical setup which will generate the same bubble, you find that there is a lot of difference in the valving efficiencies, and that is exactly why conventional means are not very well suited on the micro scale, and rather you prefer doing something which is non-conventional, like let us say electrochemistry based or magnetic based or electrical field based, to prevent this extra amount of work which needs to be asserted for translating into the micro scale. Okay, so therefore we always fetch for rather non-conventional systems for doing actuations in this scale. So let us do this example here. We have an electrochemical valve as we just described above, which is based on the principle of electrolysis of water, and essentially here if you look into we have to determine the energy required for generating an electrolysis spherical bubble with an approximate diameter of 28 microns. Okay, and we have to compare it to a similar bubble generating thermal mechanism which generates by evaporation of water of the same size. Some parameters given are the specific density of hydrogen and oxygen at 1 bar pressure and 25 degrees Celsius. It is 0.08988 kg per meter cube and 1.429 kg per meter cube respectively. The surface tension of water is assumed to be constant, and that is taken as 0.072 nanometers. The enthalpy of formation of water is about 285.83 kilojoule per mole, and some other thermodynamic properties of the liquid like water like at 1 bar pressure, like for example the U or the internal energy at 25 degrees Celsius, that at 100 degrees Celsius, sorry, this is the volume, this is the specific volume. So very specific volume at 25 degrees Celsius, internal energy at 25 degrees Celsius, and similarly the specific volume at 100 degrees Celsius and internal energy at 100 degrees Celsius are given. And basically specific volume, again let me reiterate, as the units here indicate, is volume per unit mass. So you have say 1 kg of mass of both hydrogen and oxygen or other gases, you really find out how this 1 kg would be able to occupy in terms of volumes. So that is why I kind of make a common base or a common denominator and see a volume comparison based on that. So that is called specific volume. It is different than the normal volume, it is per unit mass or per unit weight. So let us see what the differences really are in terms of energy requirements and whether they are any different if it is thermal as opposed to electrochemical. So let us first do the thermal, the electrochemical part. So if we assume a zero contact angle bubble, or let us say a perfect sphere, okay, there is no contact angle whatsoever, the pressure inside the bubble can be estimated as delta P equal to twice sigma by r. Sigma is the surface tension of the bubble and r is the radius of curvature of the particular bubble. Okay, in this case it is sphere, so it is essentially the diameter by 2. So it is 4 sigma by h really, and as we know from the example here, the diameter of the bubble is approximately 28 microns, which makes the radius about 14 microns. So here the surface tension force, as we know, is about close to 0.072 Newton per meter for water molecules, and the radius of the bubble is about 28 microns, which makes the pressure gradient. So this is essentially the internal pressure of the bubble. Okay. So 4 times of 72 10 to the power minus 3 by 28 10 to the power minus 6. Okay. So this comes out to be about 10 to the power 5 pascals or 1 bar pressure. So so all the properties are really defined at 1 bar. So therefore we can find out the specific density of the electrolysis gas mixture of hydrogen and oxygen at 1 bar pressure. So let us go ahead and do that. So all properties are defined at 1 bar. So the specific density of the mixture of gases can be obtained as specific density of oxygen at 1 bar pressure and 25 degrees Celsius times of specific density into 2 of hydrogen divided by 3. So this comes out to be equal to 1.429 kg per meter cube plus 2 times 0.089 kg per meter cube by 3. It is further about 0.536 kg per meter cube. So that is what the specific density of the gaseous mixture is in this particular case. So the amount of water required for generating the bubble would be actually equal to this particular specific density times of the volume of the bubble which is needed. Okay. This much amount of water, if you assume a continuity between the two phases, would have to be essentially decomposed in order to create an equal volume of the gas mixture H2 and O2, which would formulate a bubble. So let us just write this presumption again here. So the amount of water required for generating the bubble is m equal to V times of rho mix, which is 4 by 3 pi times of r cube times of 0.536, which is the density at this particular pressure and temperature. Okay. So this comes out to be equal to about 6.127 10 to the power of minus 15 kgs. So effectively you are actually electrochemically converting about 6.127 femtograms of mass in order to get a bubble which would have a pressure differential of about close to 1 bar. Okay. And at that particular gas mixture density at 1 bar pressure at about room temperature about 25 degrees Celsius or so. Okay. So with this it is convenient to assume in terms of number of moles how many moles of water would be needed of so many kgs of water that has been generated here to be electrolyzed for creating the bubble. So the number of moles in this case N will be equal to mass by mass of H2O, which is 6.127 10 to the power minus 15 by 18 or about 0.34 10 to the power minus 15 kilomoles. That is how the number of moles of H2O molecules would be needed to make a volume which would support a pressure differential of about 1 bar. Okay. So as we also know from the question here, the enthalpy of formation of water, if you see in this region, and this is actually the electrochemical enthalpy of formation, is actually 285.83 kilojoule per mole, okay, of material. And we already know how many moles have to be made. So, the total amount of energy which would be needed for making the electrolysis bubble essentially is nothing but this enthalpy of formation times of the number of moles. And so, therefore, if we write that down, we have the energy required for making the electrolysis bubble is essentially equal to 0.34 10 to the power of minus 12 moles times of 285.83 10 to the power of minus or 10 to the power of 3 joules, which is also 97.2 times 10 to the power of minus 12 joules. So, effectively this much amount of energy is needed to realize the total volume of the gas mixture in form of an electrochemical bubble. So, this is of course the electrical energy. This much energy has to be given externally through the electrodes to the water for it to be electrolyzed and creating this gas mixture. Let us also compare what would happen if instead of electrochemical means you have thermal mechanism to formulate the bubble. So, you have a change of phase essentially, and that creates the bubble. So, let us compare what is the energy difference in both the cases. So, therefore, if we compare the specific volume of water vapor at 100 degrees Celsius and compare that with the mass in order to find out how much amount of thermal energy would be needed to convert that mass to make a thermal bubble, we should be able to have a comparative between the total energies in both cases. So, let us say that the specific volume of water vapor at 100 degrees Celsius is about 1.673 meter cube per kg. The mass of water therefore m is also given by V by nu. The specific volume is essentially 4 by 3, 3.14, 14 10 to the power minus 6 by 3. This is essentially the volume of the sphere of radius 14 microns, so diameter 28 microns, which is the size of the bubble, divided by the new value which is 1.673. This is essentially the specific volume of water vapor, okay, which is actually given in the numerical example, the question at the very beginning. So, as you see here, specific volume of the water vapor at 100 degrees Celsius is given to be 1.673 meter cube per kg. Mind you, the thermodynamic state that we have to consider for the bubble to be shaped up is that the water vapor essentially is at 100 degrees Celsius, which is also the boiling point of water, okay, and we need to formulate the vapor in order to realize the bubble. So, therefore, all specific volumes etc. Which are considered really are at 100 degrees Celsius. So, let us try to look at that figure here and see what the mass would effectively be. So, in this case the mass comes out to be about 6.867 10 to the power minus 15 kgs, and essentially if you ignore the heat losses from the system, we assume that the system is hermetically sealed again. We can find out the energy required, the thermal energy required for formulating this amount of water vapor mass, 6.867 10 to the power minus 15 kgs of water vapor mass. So, how do we do that? We know that delta U thermal, the amount of internal energy that needs to be supplied for converting a water sample from 25 degrees Celsius all the way to about 100 degrees Celsius, is also given as the mass that is needed to be converted in kgs divided by the internal energy at 100 degrees minus internal energy at 25 degrees Celsius. And if you look back in the example, both these values are given here as internal energy at 100 degrees is about 2506.5 joules, and that at 25 degrees is about 104.88 kilojoules per kg. And so we are multiplying the mass in kgs, so we are left with this equation which is in kilojoules of energy. So we reduce this to 6.867 10 to the power minus 15 times of 2506.5 minus 104.88 times 10 to the power of 3 joules. Okay. So it comes out to be 1.64 10 to the power minus 8 joules. And so essentially that is the amount of thermal work that is needed to be done for creating this particular bubble in this example. If you may compare this value with the electrochemical energy which is needed, it is almost 4 order of magnitudes more. In the electrochemical sense it is about only 10 to the power minus 12 joules, whereas in the thermal sense it is about 10 to the power minus 8 joules. So the thermal means of course is about 10 to the power 4 times more than the electrochemical means, and so definitely you can understand which one is a better or a more energy efficient process. So let us also compare the efficiency by considering this bubble to have done a work of expansion and trying to compare that with the amount of energy that has been given into the system in terms of the work done and the internal energy change, okay, the total energy which has been given to the system. So if we do that, we can get a comparative, and we will compare both cases, the electrochemical as well as thermal, and see which one is a more energy efficient process in terms of what is going in and what is getting formulated as a result of it. So let us say that in both cases there is a work of expansion which is done by the bubble, and this work is essentially integral PdV. Also this varies between 0 and 14 microns of course, and you have a delta P here. The pressure difference is about 2 sigma by R times of the elemental volume, as I had done way back before in case of spherical symmetry, is given by 4 pi r squared dr. You can consider this by creating the volume between r plus dr and r, an elemental volume between these two components. So you have r plus dr cube minus r cube, and this effectively boils down to 3r dr times of r plus dr. The r cube goes off, dr cube is too small and goes off, dr square here goes off, you are only left with 4 by 3 pi times of 3r square dr, and that is essentially 4 pi r square dr. So that is the elemental volume dV. Okay, I am just trying to recall what we did earlier in one of the examples earlier. Okay, so let me just rub all this before we start with the derivation of the total amount of work which is done. So the work done in this case is of course delta P dV, which is essentially equal to 2 sigma by r times of 4 pi r square dr. Okay, and this varies between r between 0 and 14 microns, and if you calculate this expression here with the sigma value which is already given in the numerical problem as 72 10 to the power of minus 3 Newton per meter, you are left with a total amount of energy or work done as 1.772 times 10 to the power of minus 10 joules. Okay, that is how this total work done would translate into. This is the PdV work, mind you, as the bubble is expanding against an internal pressure of 2 sigma by r, and we assume the r to be variable here. The amount of work that the bubble would do in the process of expanding against that pressure or expanding against that delta P is essentially delta P times of dV, the change in volume. And so let us assume that the efficiency of electrochemical production of the bubble process, so electrolysis process in terms of bubble growth is essentially, let us call it Nlet is the W work done divided by W plus delta U electrochemical, which was in the range of 10 to the power minus 12 joules, as if you may remember. So this comes out to be equal to 1.77 10 to the power minus 10 divided by 1.77 10 to the power minus 10 plus 97.2 10 to the power of minus 12. Okay, let me write this in a little better manner. So it is 97.2 times 10 to the power of minus 12, and so this efficiency comes out to be roughly 65%. Okay, if you just do this calculation here. However, if you look at the thermal efficiency in generating the bubble, let us call it N therm is equal to work done divided by work done by the small sphere times of the internal energy change by thermal means required for generating that amount of or size of gases which can cause the bubble to be about 14 microns in diameter. So this would come out to be equal to essentially 1.77 10 to the power minus 10. This does not change, the work does not change in both cases, plus divided by 1.77 10 to the power minus 10 plus 1.64 times 10 to the power of minus 8, and this comes out to be equal to about 1.06%. So there is almost a 60 times change in terms of percentage efficiency when you talk about the difference between electrochemical and the thermal processes. Okay, so definitely electrochemical processes are much more efficient than the corresponding thermal processes. So let us look into another form of valves which is also known as the capillary force valves in the next example. Here this effect is called the electrocapillary effect, and you have to really understand what that is. So you can call it several other names like electrowetting effect, and essentially it happens because the surface tension essentially changes between two immiscible conducting liquids or between a solid surface and a liquid just by varying the potential difference between these. So here, as you are seeing, this is a uniformly distributed bubble with a double layer across it. You have some positive charges coming here and some negative charges outside this bubble here. So if you just apply a potential difference along this direction, maybe, okay, this is the negative end, this is the positive end, there is a tendency of the charges to kind of redistribute, and the surfaces suddenly come in more tension or less tension depending on which side it is facing. In this particular case, as you see, the charges kind of, the positive charges kind of go back like this, right, and so therefore there is a more surface tension suddenly which comes in this particular domain here. Had it been negative charge inside, the surface tension would have come in the opposite domain here. So because of that, there is a tendency of this bubble to move forward and backward just because of the change in surface tension. Now this can be done electrically, this can also be done thermally, as I will show in the next illustration where we are talking about thermocapillary effects. Okay, so what will happen here is that, as we already know, that there is a formation of an electrostatic double layer between any two surfaces. Now this may be a surface of a fluid or another fluid and a surface, and if you change the electrostatic potential in this case between the double layers, the surface tension between the two liquids would become sigma new value, which is equal to sigma old minus the amount of capacitive energy that you are pumping into the system, half CV minus V0 square. V0 is the initial value of the voltage at which the double layer exists, and V minus V0 is the differential change in the in the voltage, which causes this non-homogeneous charge distribution across the surface, causing a differential tension. C of course is the capacitance per unit area of the double layer, okay, and V is the applied potential across the liquid interface. So as a result of which there is a movement of this particular effect possible, and suppose this is going to block a capillary, you just need to ascertain that you apply a field in the direction of the capillary so that the bubble goes and blocks the capillary opening. If you reverse the field, the bubble comes out and lets the flow go out. So this is essentially how capillary force valves would work with, okay. Another very interesting example is the thermocapillary effect, as you can see here. The same effect that has been done with an external field can also be done with temperatures. So in this effect there is a temperature dependence of surface tension which is utilized for moving the fluid around or moving the valve around, which is essentially a bubble, and the surface tension really reflects the true state of surface energy of a particular structure, maybe a bubble or an air bubble or a water bubble in oil, etc. So at a higher temperature the molecules of the liquid moves faster and their attractive forces become smaller because there is less boundation because of more kinetic energies, and therefore the surface tension definitely gets affected and becomes lower when the temperature is higher, and there is a difference or a gradient in surface tension which would cause the bubble to move towards the lower surface tension. The smaller attractive force causes lower viscosity, lower surface tension. At the right side, in this particular instance, say the temperature is hot, as you can see, right. So this T2 here is much more than T1, which is the colder side. So the surface tension is lower here, and this causes a pressure gradient across the bubble which leads the bubble to move from left to right. So the bubble actually starts moving in this direction towards the hotter side because of the low surface tension. In any case, any body in this universe, as you know, always prefers to go from a high energy content to a low energy content. Surface tension is a surface energy parameter, and so if the surface tension is lesser, the bubble would definitely try to go towards the lesser surface tension which is given by this temperature gradient between T1 and T2. So very interesting effects. In fact, there is a group at NUS which works in making these bubbles to flow around in microfluidics based on these differential heating. However, one constraint that such thermocapillary effect, although it is an immensely useful effect in almost all situations, but particularly in the bioassays the problem comes because the kind of temperatures that you are talking about for changing surface tensions are pretty high, in the range of about 90 plus. Most of the biological entities do not survive this kind of temperature, and therefore especially for biological applications thermocapillary effect may not be that prominently used. However, the electrocapillary effect is definitely, or electrowetting is definitely a very widely used area for biomems based applications. So let us look at now a different paradigm altogether, which is the world of micro pumps, okay. And essentially I would like to describe here some of the basic definitions about what micro pumping is. I would like to categorize into different mechanisms. Again, there are passive and active micro pumps, there are mechanical, non-mechanical pumps essentially, and of course their actuation principles or operation principles are based on totally different physical properties or physical effects, and so therefore one important point to mention here is that whatever technology has been developed for micro valving mechanisms can be very well translated directly into micro pumping. The idea is that if you have some kind of a peristalsis motion where you have a travelling contractile, you could discretize that and make a set of 3 valves to do identically in a particular sequence this blocking action of flow at different points to build up a pressure, move along that pressure and release that pressure, and again start building that pressure on a small channel. So whatever mechanisms we have done for valving can be sequenced in a manner so that you can make those mechanisms to flow fluids around. So micro pumps can be categorized based on the principles by which energy is applied to the fluids. They can be categorized as mechanical and non-mechanical, and mechanical pumps include classifications based on the principles by which mechanical energy is applied, okay. So, all mechanical pumps however are either categorized as a dynamic pumps or displacement based pumps. So, there is some moving component, some moving member, some moving membrane which is in close proximity to the fluid that you are moving. So, that is why they are dynamic and displacement pumps. Displacement pumps again is that when the energy is periodically added to the application of force to one or more movable boundaries of any number of enclosed fluid volumes, and this results in actually a discrete increase in pressure along the direction of valving close, and the fluids keep moving that particular direction. So, examples could be check valve pumps, peristaltic pumps, valveless rectification pumps, and I am going to go into detailed principles of all these pumps just in about a little bit, rotary pumps, etc. These are some of the examples. Dynamic pumps on the other hand are where mechanical energy is continuously added to increase the fluid velocity within the machine, okay, and the higher velocity at pump outlet increases the pressure, and therefore, there is a back pressure concept which comes out in these kind of pumping mechanisms. Such mechanisms can be categorized into centrifugal pumps, ultrasonic pumps, etc. Okay, so now let us describe some of the non-mechanical pumps or types of pumps. So, essentially as I told you before, these really add velocity to the fluid by adding momentum to the fluid by means of converting another non-mechanical energy form into kinetic energy. So, while mechanical pumping is mostly in the macro scale, the second category discovers its advantages in the micro scale. There are various forms of non-mechanical pumping, or there are various principles of non-mechanical pumping. It could be a pressure gradient driven flow, as in surface tension driven flows, electrowetting, the Marangoni effect, which I showed in case of thermocapillary valves about some time back, and also pressure gradient created by surface modification. You can create a hydrophobicity gradient, and that could help in transporting water towards the hydrophilic side from the hydrophobic side. So, that is one of the mechanisms, non-mechanical pumping mechanisms. Another is concentration gradient driven mechanisms like osmosis. If you have a charge concentration and you have detailed, you have seen the details of such kind of pumping mechanisms before while doing electrochemistry. So, essentially semi-permeable membranes, surfactants, they would cause this kind of charged double layer along the surface in the solution and a diffused layer, and this layer can help you to kind of move ahead the flow of fluids as a plug through channels. There are some other ways and means of non-mechanical pumping. Electrical potential gradient is one of them. Also you have electroosmosis, electrohydrodynamic flows, electrophoresis, dielectrophoresis. These are all mechanisms where electrical potential gradient would be used for non-mechanical pumping. Then you have magnetic potential driven micro pumps like ferrofluidic pumps or magnetohydrodynamic pumps. Essentially here, as you will later see, there is an oil emulsion of ferrous particles which act as a plug and can be moved as a piston for driving ahead the meniscus of fluid. The magnetic assembly is moved back and forth by using external magnets sequentially fired in a manner so that it can move the magnetic plug back and forth. So, these are some of the non-mechanical bases of micro pumps. So, you have now categorized pumps into displacement types, dynamic types. These are the two mechanical kind of pumps, and then several other non-mechanical pumps based on varied pumping principles. Let us look at some of the comparative flow rates of these micro pumps as illustrated in the figure below here. Typically mechanical ones are the most flow rate ones. You have a higher flow rate definitely in mechanical pumps. Non-mechanicals, mechanical pumps are actually low on the flow rate characteristics. That is because the amount of energy density that you may have to add per unit displacement or per unit volume displacement of fluid is comparatively higher in this case. The energy requirement is higher in this case. So, if you look at in terms of ml per minute or in terms of flow rates of different pumps. The mechanical ones are categorized here onto the right side of this particular scale. This could include check valve based peristaltic micropumps, valveless rectification pumps, and I am going to describe these in just about a little bit. So they are more based on the 10 to 1 microliter or milliliter per minute range, high flow rate range. On the other hand, new pumping principles which are non-mechanical like electrokinetic pumps, electrohydrodynamic pumps, magneto-hydrodynamic pumps and ultrasonic pumps, they are more towards the left of this figure. It starts from about 1,000th of a mil per minute to all the way to about tenths of a mil per minute or so. So definitely as you see here, the mechanical pumps are much more in terms of flow rates. So they can couple the energy, or they can put really a high energy density to the flow for a flow rate to be higher. The novel effects, however, have lower amount of density that you can pack. It may be an efficient process, but at a time you may not be able to pump that much density because of limitations related to properties of the materials which you are flowing, essentially, or the fluids that you are flowing. So that is in a nutshell what the categorization is in terms of flow rates. So the parameters which are most important to define specifications of micro pumps are essentially the maximum flow rate, okay, and quantities like maximum back pressure. And mind you, the back pressure is developed because you are constricting the forward flow into a very small venturi or a very small outlet, and definitely it is going to take some work for the pump to do for pushing the fluid through this small outlet. That generates a back pressure onto the system, okay, and essentially whatever the pumping mechanism be, it has to overcome this back pressure by the application of mechanical or non-mechanical energy, and only then the pump can be a forward directional working micro pump. So specifications of course would include maximum back pressure. The pump power is very critical, and also the pumping efficiency is very critical. As you saw in the electrochemical case, in case of valves, the electrochemical valve has more efficiency, it's about 65% in comparison to thermal, which is only about close to 2%, okay. Some other parameters for pumps are maximum flow rates that the pump can accommodate, which is also known as pump capacity. So it's essentially the maximum discharge volume Qmax in terms of centimeter cube per minute per unit time delivered by the pump, assuming that there is a zero back pressure, okay. So if you are just letting the fluid go into an open atmosphere, then whatever amount of flow rate can be generated is really the maximum flow rate that the pump can generate. You can also categorize the pumps in terms of the maximum back pressure. It is also the maximum pressure that the pump can work against. It can still keep working if you keep on increasing the back pressure. At a certain pressure it can fail to work or deliver fluid anymore. So that is essentially the maximum back pressure that a pump can sustain. So at this pressure the rate of flow becomes equal to 0, okay. So let us do some mathematical representation of how you can calculate these efficiency factors. So the best factor that is used here is the pumping head in terms of the pressure head that is deliverable by the micro pump. So let us say the pump head H represents the net work done on an unit weight of the liquid on passing from inlet to the outlet or the discharge tube, okay. So the H here is given by the Bernoulli's equation as the height due to the pressure, that is P by rho, the height due to the kinetic energy U square by 2g, and the potential function Z in the outlet side minus the same quantities here on the inlet side, okay. So this is essentially the difference in the inlet and outlet pressure heads, and that should come somehow as H, the outlet pressure being more. So this is the pressure delivered by the pump. So if you are delivering an outlet pressure which is more than the inlet pressure, definitely there is a head addition while the flow is going into the pump. So assuming the static head at inlet and outlet as 0, really, which means that you assume that the pressures on both sides are at atmospheric pressures, and the velocities really are similar on both sides. You do not assume a velocity gradient. So in that case the maximum height that this particular configuration can accumulate, or the pressure head that it can give maximum, is equal to the potential at the output side minus the potential at the input side due to the pressure, okay, due to the position. So if a pump is kept like an incline and Z input is more than Z output, output is more than DC input. So, there will be a definite head which comes because of that. Okay. So, that is essentially some of the parameters of the micro pumps which are considered for designing such systems. So, based on the maximum flow rate of the micro pump, the maximum back pressure P or the maximum pump head H max, you can really calculate the power, the maximum power that the pump can deliver. Okay. And as you know, power is essentially nothing but pressure times of discharge by 2. Okay. This is the average power, because if we assume the discharge to be 0 and after application of the pressure head P by the pump, the discharge, maximum discharge to be Q max, the average flow rate really is 0 plus Q max by 2. And so, pressure times of the average flow rate is essentially nothing but the work done per unit time. You may remember that pressure into volume, or PdV, is the work done in joules, and Q is essentially volume per unit time. So, essentially this is power, the work done per unit time. So, the power of a pump here, assuming P max to be the maximum pressure, Q max dash to be the maximum flow rate, and assuming that the flow rate starts from 0 and gets this height as the fluid passes through the whole pumping chambers or the pumping system. So, Q max by 2 effectively is the average flow rate. So, P max into Q dash max by 2 essentially is what makes the power. And we know that the pressure max is also represented by this height max into rho into G. So, rho G H max Q dash max by 2 is what the pumping power is. So, based on this power equations, we can define pumping efficiency as the power that the pump actually generates in terms of flows by the power that it takes in terms of actuation. So, if you have certain power delivered inside, or certain energy which is delivered per unit time inside the pump, which causes the mechanical or the non-mechanical actuation of the fluid, and then it results in certain work done by the fluid flow against the pressure head, etc. So, these two essentially, the ratio between them would determine what is the pumping efficiency as to how much amount of energy which you are packing in is densified as energy applied for flow inside the pump. Now, here is an example that I would like to illustrate. So, you have a thermopneumatic system of check valve pump which delivers a maximum flow rate of 34 microliters per minute. There is a maximum back pressure of 5 kilopascals which is generated, and because it's thermopneumatic, you are essentially heating the fluid. The heater resistor here is about 15 ohms, and the pump works with a symmetric square signal with a maximum voltage of 6 volts at 0.5 hertz. So, you have to determine the pump efficiency. So, let us go and solve this particular example. So, we assume first, or we calculate first the pumping power. Okay. So, the power of the pump is really equal to P max times of Q dot max by 2, right. P max here is about 5 kilopascals, that the total maximum back pressure against which the flow rate has to be working. So, 5 10 to the power 3 pascals is what the P max is. Q dot max is essentially the maximum flow rate, which is about 34 microliters per minute. So, I can write that as 34 10 to the power of minus 9 meter cube divided by 60 for the per second into 2. So, this comes out to be equal to about 1.42 10 to the power minus 6 watts. That is what the power of the pump is. So, considering only the active half of the drive signal, the dielectric power. So, basically if you see here, what he is saying is that you have a square wave or a square signal to operate with a maximum voltage of 6 volts at 0.5 hertz, which means that for the other half cycle the power is switched off to 0. So, it is between 0 and 6 volts. So effectively the power cycle is only about half the times, and the total amount of voltage given is 6 volts in that case. The other half, which is about the remaining half is about 0 volts. So it is just a square pulse or a square wave which is given to control the heaters for the pressure rise or the thermonumeric force which would close and open the particular valve. So the electric power input here which causes the actuator power is half V square by R. V is 6 volts, half because the half cycle is only the power cycle, the remaining half cycles are 0 volts. So there is no power delivered essentially from the source into the chamber, the numeric chamber, thermonumeric chamber. So this comes out to be equal to square of 6 times 2 times 15. The resistance, mind you, is about 15 ohms, as has been illustrated in the example here. Okay, so this comes out to be about 1.2 watts. So that's what the actuation power is. So pumping efficiency is defined earlier, is essentially the power of the pump, which we just calculated in the top, divided by power of the actuator. This comes out to be 1.42 10 to the power minus 6 by 1.2, which is about 1.18 10 to the power of minus 4%. Okay, so that is what the pump efficiency is. It's pretty low, the pumping efficiency in this particular case. Thermodynamic effects in fact don't really give a lot of efficiency, because and also they are awfully slow. Their response rate is very slow. So let us now talk about the second kind of mechanism, which is peristaltic micropumps, and I would like to show some illustration from one of the research modules that we have developed in our laboratory here. So this right here is the example of what a peristaltic pump would typically do for fluid transport. So let me just reiterate, peristalsis is the motion of a traveling contractile, fluid due to a traveling contractile. So if you think that you have, let us say, a silicone tubing or something like a flexible rubber, and you are pushing this rubber from both sides and there is a fluid column in between, the fluid is almost going to be squished on both sides. Now with these two pushed, if you just go along the pipe, you are pushing the fluid along the directions of the two pushers. Okay, and that is what causes pumping to happen or pumping to occur. So that is called peristalsis. It is a traveling contractile. Similar mechanisms take place within the human body, where intestines are used to generate enough motion for pumping bile out of the human system. Okay, so we can use this traveling contractile mode as a continuous process, or we can probably discretize it, which is more suitable for the MEMS architecture. So what we have done here is that this effect has been successfully utilized to control flow of fluid motion, and that has been done by discretizing the peristalsis action in this particular illustration here. So the device made is a 3-layered device with a layer at the bottom, which you cannot see here, but it exists. Okay, so there is a layer at the bottom, there is a channel layer on the top, and then there is a blister pocket which is on the top of all this, and these blister pockets are all connected through an air circuit which is controlled selectively using a solenoid motion. And the idea is that you actually inflate and deflate these blisters in a sequence, so that you can press say for example this region here, which squishes out the fluid in both directions, and then after this forward momentum is gathered, you keep this closed so that the fluid cannot rush back, and close on the second. So you start compressing the channel on the second. So here the fluid cannot rush back, this path is closed, and the only forward direction momentum would be implied onto the fluid channel. Mind you, this green layer here indicates the fluid channel, and there is a layer on the bottom here which is the base or the glass substrate, and then you can have valve 2 and 3 operated, and the sequence can keep on rotating so that the flow picks up from here and goes all the way up to the outflow. These are some coin-like peristaltic pumps which have been developed. These are pneumatic chambered based pumps, and essentially these kind of shows a real picture of the fluid transport. As you are seeing here, this valve is slowly getting filled by the fluid, okay, and this valve is slowly getting empty because the fluid transports across this whole channel here through these blister pockets. These are some of the pumps in action. So the pumping rate has been categorized in the range of about 10 to 12 microliters at pumping frequency of 10 hertz, which has been attained, okay, and the pumps are essentially 3-layered devices fabricating using glass and PDMS, pretty much in the manner that we had done blisters. In this case, of course, the orientation of these chambers for pumping, the peristalsis chambers for pumping, are different, and they are energized by an off-chip compressed nitrogen supply regulated through LabVIEW. So this kind of brings us to an end of this particular lecture, and next time I would like to analyze the peristalsis effects in a little more detail with numerical approach, and try to see things like flow rates, back pressures, pressure heads which are attained by this peristaltic motion sequence. We will also look into some of the other kind of passive pumps like valveless rectification pumps or centrifugal pumps, or some of the active pumps like centrifugal pumps, etc. And then we will try to go ahead and do some of the fabrication processes for realizing how these small scale devices can be realized as MEMS using MEMS technology. Okay, thank you.